In this episode, the world's largest aircraft.
Engineers have taken some of the best elements from helicopters, aircraft, and of course airships, and wrapped them together in something that could be a complete game changer.
Taking engineering to new heights.
What we're hoping to show with this aircraft is that we can move to a whole nother level of performance for aviation.
And the pioneering historic innovations.
Woohoo! This is so cool! I love it! Wow!
Oh, that just snapped really suddenly.
That made the impossible possible. Since the birth of aviation, aerospace engineers have been creating aircraft that have pushed the boundaries. Constantly evolving technology means we are traveling faster, higher, and further than ever before, in a range of unique flying machines. However, there are some locations and operations that aircraft are yet to conquer.
One of the things we really want to be able to do would be some fairly niche operations that no other aircraft in the world could do. Things like long-range disaster relief or search and rescue.
For test pilot Simon Davies, carrying out these operations in the world's most remote regions requires something new. An aircraft that can fly for days and land anywhere.
For those sort of operations, you want something that behaves a bit like a helicopter, that can land, take off, offload cargo or refuel without any fixed infrastructure. You want something that's like a helicopter, but that can go further.
The solution lies in a former RAF airbase in Bedfordshire, England. Engineering journalist Justin Cunningham is on the scene, where history is meeting high-tech in the form of a new breed of aircraft.
This is Cardington Airfield, home to a set of aircraft that we thought had been all but extinct, consigned to the history books. But a group of engineers here want to change all that with this. The Airlander 10.
This mammoth engineering marvel is the largest aircraft in the world, and its design an aeronautical masterpiece.
Airlander 10 is actually a hybrid aircraft, which means it combines elements of being a helicopter, a normal aeroplane, and also the obvious one being an airship. It's a massive 92 metres long, 43.5 metres wide. It's nearly the size of a football pitch and dwarfs something like the Airbus A380 Super Jumbo.
Not only is it vast, for project director Nick Allman, the pioneering Airlander 10 is destined to open up new horizons.
This is a new age of hybrid aircraft. We can fly further. We can go anywhere. We can demonstrate levels of capability that haven't been seen before.
Using fixed-wing, helicopter and lighter-than-air technology, Airlander 10 dwarfs everything in the skies. Its 38,000 cubic metre frameless material hull with hypersensitive pressure control means this hybrid aircraft can stay airborne fully crewed for 5 days. 4 fixed and rotational turbocharged diesel engines propel and manoeuvre the craft in any direction. Plus, a cargo hold beneath the hull has capacity for a 10-ton payload, and its inflatable skids allow it to land anywhere, even water.
It's not like anything else anybody's done in aerospace for 50 or 60 years.
Airlander's structure is completely unique, and building it posed colossal engineering challenges. Not least, how to inflate the gigantic hull.
The inflation of the hull is absolutely critical to the structural integrity of the aircraft.
To fly safely, the gas inside this frameless hull must not only maintain its structure and provide buoyancy, but also be completely inert. Achieving this would have been impossible without the great innovators of the past. In 1670, Father Francesco Lana di Terzi came up with an invention that rightly deserved the title of Airship. But his dream never became a reality.
Oh.
In 18th century France, the Montgolfier brothers noticed how their washing billowed when drying over a fire.
Ooh.
And in 1793, they launched the first man-made flight with living passengers. A sheep called Montenciel, a duck, and a rooster. But trying it with humans, the dangers of a mid-air bonfire were soon revealed. That same year, more French brothers, the Roberts, launched the first manned hydrogen gas-filled balloon. Hydrogen balloons and blimps became all the rage. But their flammable filling meant they were always vulnerable. Fortunately, a solution wasn't far away. Mechanical engineer Dan Dickerell is in Kansas to find out how a discovery here on America's Great Plains would change airship safety forever.
The problem with early airships is they were filled with hydrogen. Here I have some hydrogen. What I'm going to do is introduce this hydrogen gas into a solution of soapy water. As the gas comes out, we create bubbles. These bubbles will be filled with hydrogen. Now, if I free these bubbles from its container, we see, they float away, which is great for airships. Let's create some more bubbles and repeat this process. Except this time, we're going to introduce a source of flame. And let's watch what happens. Here we go. Woo! All right. Hydrogen is very flammable.
Fire and hydrogen simply don't mix, making it a less than ideal gas for airships. However, a tiny Kansas town unwittingly held a solution.
This is Dexter. With a population of less than 300 people, you'd be forgiven to think that not much happens around here. But in 1903, something big was happening. A discovery was made that locals thought would transform Dexter from an unassuming outpost to a booming center of industry.
The 19th century had seen a boom in the use of flammable gas for lighting, heating, and cooking. And speculative drilling had hit a source of gas that was spewing out millions of cubic feet of the stuff each day. The townsfolk smelled a potential fortune.
The people of Dexter, they were planning to celebrate the discovery with an elaborate lighting of the well ceremony. The thought was a pillar of flame would rise up and light the sky for miles around. But when the time came to ignite the well, the gas just wouldn't burn.
Repeated attempts all failed, and the story of the curious gas that refused to ignite spread across the state. And samples soon landed on the desks of chemistry professors Hamilton P. Cady and David McFarland. Their follow-up research at the University of Kansas would lead to an astonishing discovery.
They concluded that the mystery gas was about 2% helium, a substance which had been thought to only exist on the sun. Not only that, in fact, further research concluded that helium here on Earth, underneath the Great Plains, existed in almost unlimited quantities.
Despite its abundance, engineers struggled to find a use for it, and it was left on the shelf. However, during World War I, helium came to the attention of the United States government. They were looking to replace the hydrogen used in their airships, and the new gas needed just one essential quality. Back at the university lab, it's put to the test.
You see? Yes, indeed, helium is lighter than air.
But introduce a flame.
As the people of Dexter found so many years ago, helium, it just won't burn.
With just a fraction less buoyancy than hydrogen, crucially, helium was totally inert. The military declared it a critical war material, and a solution to safe airship travel was finally found. And helium is now considered one of the planet's most useful resources.
Today, the helium that lies under my feet here in the Great Plains is used in everything from nuclear reactors to laser beams. If not for that chance discovery in a tiny Kansas town so long ago, the world that we know today might be a very different place.
In Bedfordshire, England, engineers are using this century-old Kansas discovery to great effect. To inflate the world's biggest aircraft.
The Airlander has 38,000 cubic meters of helium inside, and that's enough to provide a lot of the necessary lift to get it airborne. But inside that envelope, there's actually no rigid structure. The rigidity comes from the pressure of that gas.
But even though Airlander is filled with a lighter-than-air gas, this modern-day airship comes with a design twist.
Despite being filled with helium, it's not actually lighter than air like a lot of legacy airships might be. Its net weight is around a ton, something like the size of a small car. And the reason they have done that is they get this maneuverability and stability that you just wouldn't get otherwise. And it also means they only need to provide about a ton of thrust to get this thing airborne.
Whilst the helium maintains the aircraft's shape and creates buoyancy, drawing on fixed-wing aircraft designs, its unique elliptical hull acts as an aerofoil, creating 40% of Airlander's lift.
So because you're combining that helium, that buoyancy, and the fact it's shaped like an aerofoil, you're getting these hybrid effects. And what that means is you've got a hugely efficient air vehicle.
In August 2016, Airlander 10 took to the skies for the first time. Causing a sensation in the aviation world.
We're demonstrating that by using lighter-than-air technology, mixing it with other technologies, we can move to a whole nother level of efficiency. This aircraft is going to show capabilities that no other aircraft have got.
Airlander 10 is pushing the boundaries of aeronautical technology. But if this aircraft is to join the greats of aviation history, its engineers face many more challenges.
Just look at this place. This is somewhere where history truly was made. This is Hangar Y.
To produce more impossible engineering. Hybrid airship Airlander 10 is the world's largest aircraft. Built for endurance, this 92-meter megaship is taking the aviation world by storm. Test pilot Simon Davies will be at the controls.
As a test pilot, being involved in the first flight of a completely new class of aircraft, it was a career high for me. Really couldn't be better. There's something quite magical about it. It's a very exciting experience just to be around it.
Designed to operate in environments other aircraft can't sustain, Airlander 10 can cruise at 150 kilometers an hour stay airborne with a full crew for 5 days, and without crew for up to 3 weeks.
What engineers have done here, they've taken some of the best elements from helicopters, aircraft, and of course airships, and wrapped them together in something that potentially could be a complete game changer for the industry.
This resilient craft can take off in 35-knot winds, but as it rises to altitudes over 6 kilometers, its non-rigid helium-filled hull faces a major potential problem.
As atmospheric pressure changes, and really critically as we climb and descend, the external pressure changes as well, and we have to maintain the hull at a constant differential pressure between the gas inside the hull and the environment, otherwise the envelope could expand and rip, or the envelope could collapse.
So how do you control the hull pressure of the world's biggest inflatable flying machine? The solution is over 150 years old. Physicist Andrew Steele is in France in search of a hidden location that was the site of a major historical breakthrough in aeronautical engineering. In the 1870s, audacious French engineers Arthur Krebs and Charles Renard set themselves a challenge to create the first fully controllable airship.
We're here in the Meudon forest just outside Paris, and it's amongst these trees that we can find the home of Renard and Krebs' great invention. And here it is. This is Hangar Y. Just look at this place. It might look pretty run down now, but this is somewhere where history truly was made. Behind these huge wooden doors lies the home of Krebs and Renard's pioneering airship, La France. Wow.
Completed in 1879, Hangar Y was tailor-made to accommodate the state-of-the-art 50-metre-long airship they called La France. The giant prototype airship was kitted out with the latest in aeronautical technology. But there was one innovation invented decades previously that was as yet untested. It was called a ballonnet.
So imagine that this is our airship. We've got an external bag, and then inside, this blue balloon represents a ballonnet. Now, at the moment, there's no gas inside this airship, and that means, obviously, it's heavier than air, and so it just sinks. So if you want to make this thing take off, what you've got to do is fill it with some lighter than air gas. And I've got a tank of helium just here. There we go. Now this thing is just starting to be buoyant, and so the pilot has got just enough of that buoyancy to take off.
When La France gained altitude, the external air pressure decreased. That meant the gas inside would expand and potentially burst it.
That's where this balloon comes in. We can stick some air into here.
Having a ballonnet filled with air within the outer bag means that, as the gas expands,
Whoa, there we go.
air can be released
You can just let some of the air out of this internal balloon.
to give the gas more space,
There we go.
meaning the pressure between outside and inside can be regulated. Previously, one airship pilot had to resort to slashing a hole in his flying machine in order to prevent it from popping as it ascended. But in 1884, the experimental ballonnet system meant La France could exit Hangar Y and successfully take to the air over Paris for what is now considered the first fully controlled free flight.
Krebs and Renard's record-breaking airship was floating in these very skies almost 150 years ago. It was their taking this simple innovation and putting it into engineering practice that revolutionised lighter-than-air travel forever.
In Bedfordshire, England, Airlander 10's engineers have taken Kreb and Renard's ballonnet system and supersized it.
To give you some idea of the scale of them, they start in line with the scene that you can see just running up and down the hull. And the forward ballonnets go all the way back to the forward propulsor. And typically on the ground, they're 8 meters high, so it's like probably 2/3 of the height of the aircraft. So they're absolutely cavernous.
Concealed within hull compartments, Airlander has 4 giant air-filled ballonnets. As it takes off, a sophisticated venting system forces air out, allowing the helium to expand, maintaining a constant pressure between the inside and outside of the hull.
We have a fixed amount of helium. As we climb and descend, that helium expands and contracts, and we account for that expansion and contraction by the large air ballonnets.
And this happens automatically.
We're underneath the forward right ballonnet, and this is the valve associated with that ballonnet. So as we climb, these valves will open under spring pressure and let some of the air out to maintain the hull at constant pressure. If I pull on the valve, you can hear some of the air rushing out. And the valves pop closed again.
When descending, the ballonnets are increased in size as the helium compresses.
Over here, one of the key devices is a fan, which we use to pump air into the ballonnets as the aircraft descends. So you can just hear in the background the fan running now. It's pumping quite a high volume of air into the ballonnets just to top up pressure.
By evolving the ballonnet technology from the past, Airlander 10 can stay airborne for an unprecedented 5 days with a crew and potentially up to 3 weeks unmanned. But to land in some of the most inhospitable locations on the planet, its designers must turn to yet another iconic innovation from the past.
This is such a privilege to be flying in this absolutely iconic, brilliant machine.
To create even more impossible engineering. For many, airships were a thing of the past. But engineers in Bedfordshire, England are dispelling that myth. With Airlander 10, the world's largest aircraft. Project Director Nick Allman is at the heart of this aeronautical enterprise.
What we're hoping to show with this aircraft is that by adding some different technologies together, we can move to a whole nother level of performance for aviation.
One of Airlander's key remits will be to carry out operations in the most isolated locations on the planet. Capable of delivering supplies, 10 tons of cargo can be stored in the 45-meter payload area, fixed beneath the hull. But landing this cargo in these environments is another matter, creating a huge challenge for test pilot Simon Davies.
For long-range logistics or operating out of remote, unprepared areas, the ability to land in confined areas would be a huge advantage to this aircraft. We really would want a vertical landing capability.
So how do you hover a 92-meter-long aircraft and land it with pinpoint precision? It's a task that would have been impossible without more great engineers from the past. Even Mother Nature finds hovering difficult. Only a handful of creatures can do it, and only one, the hummingbird, can fly backwards. Throughout history, man has attempted to imitate this very useful skill with various degrees of success.
Bravo!
But from Da Vinci's flying screw to the jetpacks of the 60s,
That's left me shaken.
none have taken off like one of the 20th century's greatest inventions.
Woohoo! This is so cool! I love it! Wow! This is such a privilege to be flying in this absolutely iconic, brilliant machine.
Dr. Rhys Morgan is soaring high above the British countryside in a helicopter that changed the aviation world, the Bell 47.
This particular model of the Bell 47 is actually 47 years old, but it doesn't really differ that much from the original model that was designed back in 1945. This helicopter marked a milestone in popular aviation, but it owes a great deal to a pioneering engineer who just a few years earlier made a game-changing design breakthrough.
Born in the Ukraine, Igor Sikorsky had been experimenting with the rotary wing concept since 1909. It was a complex aerodynamic challenge that continued to foil both him and his peers.
Helicopters fly by having blades that rotate at really fast speeds around a single axis, and that creates lift. But early helicopters suffered from really bad stability and control issues. And that's because as the blades are rotating at such high speeds, they're generating huge amounts of torque or turning force. So as the blades spin one way, the fuselage wants to spin the opposite direction. And that makes it really uncomfortable and very, very difficult to control.
Engineers experimented with different rotor configurations with mixed success. It would be Sikorsky who took the best innovations on offer and combined them to make the world's first viable helicopter.
What Sikorsky did was have a single main rotor with a tail boom supporting a smaller anti-torque rotor, which counteracted the fuselage's natural tendency to rotate in the other direction. As the main rotor spins in one direction, the smaller tail rotor spins in the opposite direction, producing a counteracting force to stabilize the fuselage. It really transformed these flying machines.
This combination of technologies demonstrated in Sikorsky's VS-300A created a blueprint for all further rotary-winged craft to come.
Sikorsky's breakthrough made the helicopter more than just an engineering flight of fancy. For the first time, it was stable, practical, and truly maneuverable. But it was Sikorsky's main competitor, Larry Bell, that took this concept and planted it in the public imagination.
Designed by Larry Bell's engineer Arthur M. Young, the Bell helicopter was the first to be certified by the civil aviation authorities.
It was Larry Bell's vision to create a flying car for the masses. They've been used in all sorts of ways, from crop spraying to delivering mail. Thanks to its ability to land on a sixpence and hover into areas that just were not previously possible, the Bell 47 transformed how people thought about air travel. And its full bubble cockpit design would define the shape of helicopters for years to come. Does that sound about right? Ah, look at that. It's doing hands-free.
Airlander's team are drawing on the physics of helicopter flight to maneuver an aircraft the size of a football pitch. Test pilot Simon Davies can use what's known as vectored thrust to lift this supersized craft, courtesy of two rotating engines.
If I select the vectors 20 degrees up, and then outside you can see the whole duct, propeller and engine assembly now pointing 20 degrees up.
But to produce near vertical movement, Airlander's engines are equipped to do more.
So we're at the forward right engine, propulsor number 4. To be more responsive, to also achieve a greater downward thrust, we can use the vanes behind the propeller to further deflect the airflow and change the thrust on the engine.
Designers are currently working on engines capable of rotating 180 degrees, a progression that will allow Airlander to land anywhere.
We'll be able to move the vectors fully up to provide pure lift and zero thrust. and then we'll be able to fly it effectively as a helicopter and land in confined spaces.
The vision to evolve helicopter technology is setting Airlander apart from the rest of the world's flying machines.
So if we can make the aircraft behave a bit more like a helicopter, we'll be able to land in confined spaces or hover over a point to deliver underslung loads. We'll give the most possible flexibility to operators of the Airlander aircraft. So using thrust vectoring, we'll be able to do things that simply no other aircraft in the world can do.
Airlander's capabilities will allow it to navigate and land in hostile territory with extreme environmental conditions. This poses a significant engineering challenge when using an all-material hull.
Engineers here at Cardington, they needed to find a material that was up to the job. It obviously needs to be super lightweight, but this is a vehicle that needs to go anywhere, so that material needs to be super durable.
So how do you ensure this extraordinary inflatable will stand up to the rigours of extreme air travel? Achieving this would have been impossible without another of history's inspired discoveries.
Such a gorgeous little car.
Physicist Susie Shee is investigating a brilliant innovation.
Woo! Yeah!
From the swinging 60s.
Saving weight in a vehicle can make a huge difference in terms of performance and efficiency. And in the mid-1960s, around the time this gorgeous car was winning races, scientists in the USA came up with a way of doing just that. Woo-hoo-hoo! With experts predicting an impending oil crisis, researchers started to focus on trying to reduce the weight and therefore increase the efficiency of the cars. And one area they started to focus on was the steel bands inside the tyres that give them their strength.
In 1965, research scientist Stephanie Kwolek was working on finding a new type of ultra-strong polymer. After spinning one of her test solutions into a fibre, she discovered that the ultra-strong thread was almost impossible to destroy.
This new wonder material is called Kevlar, and it's revolutionised our world.
To investigate its qualities, we've come to a laboratory where they push experimental materials to their breaking point.
This is Kevlar, and the reason this material is so incredibly strong is because of both its chemical structure and the way it's manufactured. So Kevlar starts out as kind of a long, thin chain of molecules, and I can demonstrate that using these pieces of rock candy.
Each stick of rock candy represents a single strand of molecules, not overly strong on its own.
But if I want to make it stronger, what I can do is I can gather up all the different strands and then bond them together.
In a process known as wet spinning, the individual molecule strands are aligned. They extend and form straight parallel chains. In this configuration, the strands form hydrogen bonds which act like glue.
Now they're all stuck together and bonded together. So that's the theory. Let's see how it works in reality.
To put this to the test, a strand of Kevlar is pitted against a strand of steel, which is of equal size, but 10 times the weight. This tensile testing machine can pull the samples apart with a maximum force of 5 tons.
All right, so I've got my steel all set up and ready to go, and I've got a high-speed camera watching it so we can see exactly what happens when it breaks. So, all ready to go. So it's stretching apart. You can see it's straightening the wire out. Oh! Okay, there it's gone. So that just snapped really, really suddenly. If I have a look at the graph, I can see that it broke with 450 newtons of force, equivalent to about 50 kilos. Let's try the Kevlar. So it looks quite different from the steel. Just kind of looks like a taut ribbon. Oh! Ah! And as it fails, it sort of pops out. So it fails in a really different way to the stainless steel. And you can see all these broken fibres here now have no strength whatsoever. That's gone up to roughly 2,000 newtons, which is equivalent to 200 kilograms of force pulling that apart, which is about 4 times the strength of the stainless steel.
Thanks to the pioneering work of Stephanie Kwolek, Kevlar can now be manufactured so strong that it has 8 to 9 times the strength of steel, of comparative weight, and its applications are almost endless. To build the world's largest aircraft, engineers have used 7,000 square meters of high-tech material, enough to cloak the White House in Washington.
What they decided on was not one material, but 3, and I've got a sample here. On the outside, it's made of Tedlar, and that's extremely weather resistant. It's going to allow it to land on any surface, as well as protecting it from weathering and UV rays.
In the middle is a layer of mylar to contain the helium atoms. And on the inside, 50 years after its discovery, lies Kevlar's latest spin-off.
Vectran, super strong, derived from Kevlar, and that gives this structural rigidity, and you can actually see the individual weaved fabric there, just to add that directional strength that they need for this elliptical structure.
Pound for pound, this extraordinary liquid crystal polymer is 10 times stronger than aluminium.
It's a really critical component that makes this airship a success.
Airlander's innovations are making endurance flight a possibility. But to make it a reality, its designers need another piece of technology with its roots in history.
Oh, there we go, that's amazing. Wow, you can really see the laser just bouncing around.
To produce more impossible engineering. In 2016, engineers in Bedfordshire, England, launched an extraordinary addition to the skies. The hybrid airship Airlander 10 is the largest aircraft in the world and designed to fly for up to 5 days continuously with a full crew and potentially 3 weeks in unmanned mode.
In a drive for greater and greater efficiency in aerospace, we can move to a whole nother level of efficiency. And that's primarily what we're trying to do here.
As engineers prepare for the latest flight, pilot Simon Davies has the job of manoeuvring this colossal craft.
As a pilot, it's absolutely vital that you have complete trust in your flight controls, and they're going to give you the same repeatable results every single time.
With the steerable propulsors at Airlander's rear, connecting them to the joystick is an engineering conundrum.
It's nearly 80 metres from the flight deck where we are now to the back of the aircraft, so we need reliable signalling and we need to save weight wherever possible. Every gram that you can save really counts.
Electrical signalling cable is too heavy and prone to interference. So how do you provide a fail-safe signal between the flight controls and the flight mechanism? Achieving this would have been impossible without some inspired engineering from the past. Porthcurno in southwest England is a picturesque seaside location. But physicist Andrew Steele isn't here for the view. he's unearthing an historic innovation that once linked this Cornish cove to every corner of the globe.
By 1920, this beautiful little beach was the single most connected place in the world. It was the hub of the closest thing the Victorians had to the internet.
At the height of the British Empire, global telecommunications were taking off. And in 1870, the first of Porthcurno's many copper telegraph cables was laid, in a system stretching underwater for over 5,000 miles. The remnants of this ambitious system are still visible today.
Lengths of cable like this would have connected Cornwall to the rest of the world. And it's no exaggeration to say that these kick-started a communications revolution.
At the centre of this revolution was Porthcurno's tiny cable hut.
In its heyday, this is where all of the cables from around the world would terminate. Each one of these was connected to thousands of miles of continuous cable running under the ocean.
But soon there was a need to handle higher volumes of more complex information, and the copper-wired electrical network became overwhelmed. In the 1960s, 3 American scientists, Donald Keck, Robert Maurer, and Peter Schultz, were looking for an alternative. They wanted to harness the speed of light to send signals via glass fibres.
So imagine we want to send a light signal, that's this laser pen here, from this bucket down to that bucket on the floor. If we shine the laser through here, you can see a dot comes out on the wall over there. And that is because light travels in straight lines. And this is basically the problem that Keck, Maurer and Schultz were facing. Light doesn't want to go around corners, and in their glass fibres, whenever the curvature was too tight, light was escaping.
But the scientists discovered that coating the internal surface of the glass fibres with a compound of chemicals created something called total internal reflection.
Take out that bung, oh, there we are. And you can see this flow of transparent liquid is a bit like a glass fibre going around a corner. So now if we shine our laser through again, and there, whoa, there we go, that's amazing. Wow. You can actually see a green glow down in that bucket. We've successfully sent our message. Wow. It's amazing. You can really see the laser just bouncing around. And this is just like how it would pass down a glass fibre. And it's this technique called total internal reflection that Keck, Maurer and Schultz used to reliably transmit signals of light down fibres made of glass.
This new fibre optic technology had 1,000 times greater capacity and could send information 100 times further. Today, the idyllic Porthcurno continues its unlikely role as a gateway to the world, with modern fibre optics coming ashore from beneath the oceans. More than 50 years after its creation, fibre optics is governing the controls of the Airlander 10 airship, with a state-of-the-art flight system known as fly-by-light.
So when I move the stick, the signalling is, to all intents and purposes, instantaneous. There's a box that digitises the signal and measures the deflection of the stick, and that signal is then sent around 6 completely independent paths. So if we have a break in a wire, we can carry on operating the aircraft safely.
To connect the central flight deck to every corner of Airlander's gigantic hull takes over 7 kilometres of surface-mounted fibre optics.
This is the gland that contains the fibre optic cables. It's not buried behind panels, it's outside, it's accessible, it's lightweight, it's robust to the elements, and it just gives us confidence that our systems will operate reliably and repeatably every time.
As the signals fly along these fibre optics, on reaching the actuators and control surfaces, they are converted into power, driving the control mechanisms in an instant.
The scale of the aircraft, the complexity of the flight control systems, the fibre optic cables, gives us reliability and robustness in operation. It's a great solution for this aircraft.
Airlander 10 signals the rebirth of an aeronautical era that many thought was long gone.
This really is the genesis of a new generation of airships.
And this unique hybrid aircraft will open up the skies.
The process of developing our knowledge and understanding of the aircraft and improving capability all the time, it's really exciting.
Inspired by the innovators of the past.
Woohoo! This is so cool! I love it!
Adapting their ideas and making discoveries of their own. Airlander's engineers and pilots are making their mark on aviation history.
There's immense pride over the technical achievements and the things we've learned and the game-changing capability that we're bringing.
They are succeeding in making the impossible possible.
You come and show people around and they say to you, do you know what? You've got the most amazing job. So for me, working here and leading this program is the most amazing thing, a real privilege.